Okay, then we are happy to welcome today Massimiliano Tamborrino, who is Associate Professor at the Department of Statistics of the University of Warwick. He has been a researcher assistant at the Institute of Stochastics in Linz University, and he earned his PhD from the Department of Mathematics at Copenhagen. His main interest is in stochastic processes, mostly in diffusion processes, with modeling, numerical and statistical point of view. And he's expert in interplay between stochastic numerics and statistics, with applications to neuroscience, physiology, psychology, and biology. He also leads the One World ABC seminar, which is a monthly seminar on Bayesian computation and Bayesian approximation inference. Okay, Massimiliano, you can start if you're ready, please.
Yes. Thanks a lot, Wissam. Thanks a lot to the organizer for giving me the possibility of presenting my work. Thank you, everyone, for being connected. What I would like to talk about is a recent work on some numerical schemes for a particular class of stochastic differential equation where some underlying drift, where the underlying drift coefficient does not have a global ellipsis property. Okay? Let me start by quickly giving an overview of what are my interests. Wissam has already given a very nice overview of my interests. Roughly speaking, I'm interested in anything related to stochasticity from a numerical, probabilistic, and statistical point of view. I'm interested on the modeling side. I'm interested on deriving numerical schemes to simulate SD, numerical schemes to be embedded and to use within simulation-based inference or more generical simulation and inferential algorithms. And I'm interested on dealing with partially observed stochastic processes or fully observed stochastic processes, mainly from the point of view of neuroscience. And what happens is that you might have some multivariate SD, but then you only observe some of the coordinates, and this is particularly tricky and introduce some challenges at different levels, including the numerical and the statistical level. Today's setting of interest is for this semi-linear d-dimensional SDE, where what we have is some semi-linear drift. So there is this drift coefficient f, which can be decomposed into some linear component, a xt, where a is a d times d dimensional matrix, and some nonlinear terms n. Okay, so the reason why it's called semi-linear is because we are able to express the drift as the sum of some linear term and nonlinear term. And then there is some noise that is the form of what is called as additive noise. That means that the diffusion coefficient is nothing else than a matrix, and Wt is our standard multivariate Brownian motion. Okay. The drift f, while being semi-linear, it's also a local Lipschitz. That means that it's not global Lipschitz, but only one-sided Lipschitz, as I will comment and show in a second. And this non-linear term, which is the one that actually is causing a problem and makes everything interesting, this non-linear terms is allowed to grow polynomially. Okay, so overall, the semi-linear drift is not globally Lipschitz, but we assume to be one-sided Lipschitz and to have these non-linear terms that can grow, but as most polynomially. Okay. Feel free to ask if you have any question. Feel free to I don't know, virtually raise your hands or post a question in the chat. Feel free to ask a question along the talk, not necessarily at the end. In terms of noise, well, this matrix here, sigma, might yield different type of SDEs. So we will be talking about elliptic SDE if we multiply sigma times the sigma transpose, and what we obtain is an invertible matrix. Okay, so if that's the case, then it means that sigma is called a full rank. It means that the noise, the Brownian motion, enters directly in all the components of our equation. There can be cases where sigma times sigma transpose is not invertible. What does it mean? It means that if we imagine to write explicitly all the D components, all the D equation of our D-dimensional SDE, the noise will appear only in, let's say, n out of the D equation. Okay, so only in some of the coordinates. But what happens is that the overall transition density of the process x times t given x at time s, that means a transition density of full rank. Okay, what does it mean? Well, this means that despite the sigma times sigma transpose is not invertible, and despite the noise enters only in some but not all coordinates, the noise propagates throughout all coordinates, yielding a transition density of rank. I'll come back to that. Okay, and actually we are also considering the case where the drift and the diffusion coefficient are in a way that some underlying geometric orthogodicity occurs. So we are in a framework where our process has a distribution that converges exponentially fast to an invariant density. That's the idea of geometric ergodicity. And if we want to prove geometric ergodicity, there can be different techniques depending on whether we are dealing with elliptic or hyperelliptic SDEs. And in the case of elliptic SDEs, this corresponds to just checking that we are dealing with elliptic SDEs and we derive a so-called Lyapunov function. And for hyperelliptic SDE, we also have an extra irreducibility condition. Okay, so the setting seems quite general, and some of the words that I say might be not so clear to some of you or not so familiar to some of you. So that's why I want to focus on a particular example. So in fact, the whole work was motivated by this study. This is the so-called stochastic version of the Fitzinger-Gumo model. Maybe some of you knows its corresponding deterministic expression, which is obtained when these components over there as 0 sigma. Yeah? So if we set sigma to 0, this will be nothing else than the two-dimensional deterministic Fitzinger-Gumo model that we know that is an oscillatory model. We know that it has some nice properties. Now, if we are dealing with some noise term, what we obtain is a stochastic version of this Fitzinger-Gumo model. And again, there are some oscillatory underlying dynamics. The reason for focusing on this model is for one of its applications, that is neuroscience. So in neuroscience, these two components describe the membrane voltage, the VT, the first coordinate, and UT is a recovery variable. And what happens is that the underlying dynamics are having this oscillatory behavior in the VT component, in the membrane voltage. And you should imagine that anytime you have this sudden peak in the VT component, there is the release of the so-called spike. Okay? So a spike is a release of an action potential, a neural information. There is a discharge of electrical neural information across the brain. And these spikes are responsible of encoding the information. So in our brains, we have billions of spikes and billions of neurons, and they interact through these spikes. From a point of view, well, we have several things that we would like to do. Initially, we were interested in estimating some of these parameters. You see, there is a parameter epsilon. It is a time scale separation between the fast and the slow coordinate. There is sigma. It can be sigma 1, sigma 2. Well, we'll come back to that. Okay, but if we just forget about the application and we focus at the stochastic process from a mathematical point of view, well, then what we are dealing with is a two-dimensional SDE, where we see that we have something that is linear. You see, these four terms are actually linear in V and U, and then there is these terms, this -1 over epsilon V to the power of 3, that makes our drift nonlinear. So in fact, thanks to the fact that we have this drift here that is nonlinear, the overall fxt, so the overall drift, is non-globally Lipschitz, but only globally one-sided Lipschitz. That means that a condition like that is fulfilled. Okay. Remember, n of x is the corresponding nonlinear part when we split our drift into some linear components and nonlinear components. Okay. So you see, we are dealing with a two-dimensional SDE characterized by some linear drift and some nonlinear components. Okay, that's exactly the formulation that I was writing before. And these nonlinear components satisfies a globally one-sided Lipschitz condition, and the drift, the nonlinear part, is allowed to grow at most polynomially. So we are in the framework, the general framework that I was describing before. One thing that is interesting to look at is this idea of ellipticity and hyperellipticity that I mentioned before. Okay, so imagine that our sigma matrix, sigma 1, sigma 2, is having this coefficient different from 0. Well, then if we imagine computing sigma transpose, what we obtain is a matrix of full rank. Okay, it has rank 2. That means that there is a noise entering directly into the membrane voltage, the VT component, and the recovery variable UT. What is interesting, though, is the behavior when the matrix sigma is degenerate, or the matrix sigma is a 0 entry. So imagine that the sigma does not have sigma 1, but only sigma 2. So that means imagine that sigma 1 is equal to 0. Okay. What happens in this case is that if we multiply sigma by sigma transpose, well, then we will have a 2x2 matrix with entry 0, 0, 0, sigma squared 2. So that means that our matrix is degenerate, meaning that there is noise entering only in the second coordinate of our process, entering only in UT. But the funny thing, the nice results is that actually this process xt, so the joint density between our components, admits a smooth transition density. What does it mean? It means that if we try to compute the covariance of x times t given x times s, well, this covariant matrix will be well defined and will be of rank 2. So that means that somehow the noise propagates through the so-called rough component to the smooth component. Okay, so So as the name suggests, the rough component is the component where the noise enters directly. So in this case, UT. So we have this UT coordinate, the second one, where the noise enters. And actually the noise propagates to the other smooth component, so to the component without the noise, via the drift. Because if we look at here, there is this minus UT term. Okay. So thanks to the fact that the derivative of the drift component of the first coordinate respect to the rough coordinate is non-zero, the noise propagates from one coordinate to the other. When this happens, we say that SDE is hyperelliptic. Okay, so this is a very nice result. It is very common beyond neuroscience, beyond the Fitzgerald. It is very common that we have a d-dimensional SDE where the noise enters only in some of the coordinates, but still it propagates through the other via the drift. How can we see that? Well, we have this nice illustration on the effect of the noise on the Fitzgerald. Okay, what I'm drawing on top is it's one trajectory of VT. Okay, for different value, for different intensity sigma. Now, if my system was not hyperelliptic, I would have expected the VT components to be deterministic. That means that no matter what is the value of sigma, the behavior of VT won't be affected by that. But actually, you can see that that's clearly not the case. So only when sigma is zero, the VT is deterministic. In all other cases, VT is influenced by the noise. So even if the noise does not directly enters into the first equation, into the first coordinate, the noise propagates from the rough second coordinate into the first via the drift. And this is what we observe here, right? You see that depending on the value of sigma, the VT trajectory has a different behavior. And if you remember, I mentioned before that these peaks are the time, these peaks correspond to the release of the neural information. These peaks are those modeling the spike. So actually modeling this behavior and successfully capturing this behavior is crucial because it means that we are actually having some important consequences on the generation of spikes. Okay. I saw that there was a question in the chat. Okay. What you see here is a phase plot. So it's a plot of V and C. Well, actually, this should be a U. So this is a two-dimensional plot of how the trajectory evolves. A nice thing that one can prove is that also this equation has admits an invariant distribution, and actually that SD is geometrically ergodic. One can find some dissipativity condition, and if this dissipativity condition is met and the SD is elliptic, so here we have a non-zero sigma 1, then this implies that the underlying SD admits a geometric ergodic, or is geometrically ergodic. And if in the case of SDE, we have an extra condition. So actually we are asking that we start from any point X within the state space, and we have a non-zero probability of moving around the state space. Okay. So the condition for deriving for proving the geometric ergodicity of an SDE in the case of the hyperelliptic Fitzgerald have been derived in this paper by Leon and Samson that has been published in the Annals of Applied Probability a few years ago. Okay, so what I've been talking now is an example, a particular example, an important example of a semi-linear SDE with non-globally Lipschitz drift and some additive noise that can be elliptic or hyperelliptic. Okay? So if you imagine an even more general framework, we have some sort of general SDE that we can rewrite into as a sort of in the solution version. we would like to be able to simulate this trajectory, because perhaps if we want to make inference, we will need to derive the distribution of the process at times ti given the process at times ti minus 1. Okay, so when we want to do that, we need to ask ourselves, well, do we know the transition density? Do we know what is the law at the process at times t given times s? If yes, we are fine. We can simulate exactly from that. If the answer is no, the next question will be, well, can I derive some simulation scheme with the flavor of important sampling, in case this is something that is familiar to some of you? Can we derive an exact simulation scheme such that I do not know the transition density, but I can still simulate exactly? Quite often, like for example, in the case of the Fitz-Nagumo, the answer is no. So that means that we have to rely on some numerical scheme to simulate from our SDE. And whenever we do that, we know that we are introducing some error, we are introducing some approximation. So ideally, we would like to derive a numerical scheme that preserves all property of the theoretical model. First of all, the numerical scheme should be mean square convergent. So we would like to have a strong convergent numerical scheme, meaning that when the time step goes to 0, the LP distance between the true process at times ti and the numerical approximation at times ti goes to 0. And it goes to 0 with an order r that is depending on delta to the power of r. So we have strong error of order 1 if here we have r equal to 1. We have said that the initial SD might be hyperelliptic. So if that's the case for the true model, we would like also the numerical scheme to fulfill this condition, meaning that if we derive the covariant matrix of the process at time ti given the process at time ti minus 1, this would be invertible, meaning that we have a bivariate random object in the case of the Fitz-Nagumo. We would like a numerical scheme to preserve the geometrical codicity and also the model dynamics. So we were mentioning that this Fitz-Nagumo has oscillation. So ideally, we would like a numerical scheme that also preserves the amplitude, the frequency of the oscillation, and so on. Whenever you deal with numerics for SDEs, or whenever you do not have an exact simulation scheme for sampling from the distribution of xi given xi minus 1, you're always facing some sort of common beliefs that I will try to convince you that are only some beliefs, but they are not correct. The first one is that, well, if you choose a small enough time step, things will work out, okay? This is the first common belief. Another one is that, well, if you choose a numerical scheme that is convergent, everything is fine, okay? So in a way, especially, I mean, these are some beliefs that are clearly not from people in numerics, but if you talk with someone that is not working on numerics, on the one hand, there is a goal on using a convergent numerical scheme, and that's it. So once you have found a numerical scheme that is having a strong order 1 or 1.5 or 2, or as soon as you prove that it's strongly convergent, you stop it there, you're happy, and that's it. And the other thing is, well, actually, why should I bother deriving some very sophisticated numerical scheme if everything works when the time step is small enough? And I will try to convince you that this is not always the case, so one has to be careful. And the other, in a way, common belief is, I mean, does it really matter if I'm interested in doing statistics? Why should I care about this if it's just enough to choose a very small time step and a convergent numerical scheme? So let me go back. Let us consider again our general setting. So remember, F is the non-global elliptic drift, and sigma is a generic diffusion coefficient that in this case, in our setting, does not depend on the process, right? So in our case, sigma xt would be equal to sigma. So by far the most used and common numerical scheme is the Euler-Maruyama numerical scheme that is very intuitive, is immediate, and is based on the idea of, well, discretizing the underlying SDE. So this will become some sort of delta xt. So the difference between the increment at time ti and the times ti minus 1. Here we have the drift evaluated in the previous point. The dt becomes the time step, delta. This is a constant, so sigma. And then we have an increment of the Brownian motion between times ti minus 1 and ti. So this would be multivariate Gaussian with a null mean and a diagonal matrix equal, and the covariant matrix equal to the diagonal matrix times the time step. Okay, which is why we are going to rewrite this as square root of the time step and then a multivariate standard Gaussian vector. This type of numerical scheme is very common in statistics because you get for free that the transition density of the process conditioned on the previous one becomes Gaussian, right? If you have any familiarity, you will see that the distribution of x at times ti given the previous guy would be Gaussian with this mean and the covariant metric sigma transpose times delta. So it's straightforward. You get it Gaussian, you get the transition density is Gaussian. You can make a lot of nice inference based on this assumption. The problem is that as soon as you have f that is non-globally Lipschitz, as in today's setting, well, it has been proved by Martin Utzenthaler, Jensen, and Kloeden that actually this very well known and this very commonly used Euler-Maruyama numerical scheme is not strongly convergent. Okay, so no matter how small is the time step, when the time step goes to 0, there will be a difference between, so the error won't go to 0. Okay, so what was the idea? Well, the drift is the one causing me problem. I use some sort of modified Euler scheme to take into account this, to tackle this problem. One possibility was the so-called tame Euler-Maruyama scheme, which is nothing else than taming the drift that we have in the Euler-Maruyama scheme by some quantity such that we make sure that this term here doesn't explode. And there is another corresponding version, which is the truncated Euler-Maruyama scheme, where now the drift is divided by the maximum between 1 and this quantity there. Okay, so both of them are mean square convergent numerical scheme. One can prove that the order of the tame is 1, and one is, we know that it's mean square conversion, but one cannot derive explicitly the order. But again, if you look at the transition density of this process given the position at the previous time, you can see that again, this is Gaussian because this comes from this guy. Okay? So this is a Gaussian random variable with this mean or this mean and the same covariant matrix as before, sigma times sigma transpose times delta. Now, everything is nice. However, if you imagine being in the case of hyperelliptic SD, we just say that sigma transpose is degenerate. Yeah. So what does it mean? If sigma is not sigma 1, sigma 2, as we saw, for example, for the in the case of the Fitz-Nagumo, when you compute the covariant matrix of this transition density, and that's what happens, for example, for the Fitz-Nagumo, you see that what you obtain is a covariant that is not of full rank. But this is a problem, right? Because if you do the calculation for the true model, you will be able to prove that actually the full model, so if you imagine to replace the tilde with the x, or if you consider the transition density of the two processes, well, this will be a full rank. Okay, so this is the first take-home message. We have two numerical schemes, tamed Euler and truncated Euler, that are mean square convergent, so they are strong convergent of order 1, but they will never fulfill this property, no matter how small is the time step. Okay, so the belief that things will work nicely as long as the time step is small is not really the case. Okay, so this is an example where no matter how small is delta, the covariance will always be degenerate while it shouldn't. Okay, so that means that if we simulate with Euler-Maruyama, the one-step transition density won't have any noise in the first coordinate, but only in the second. And also, not only the fact that the delta is small enough will make it working, there is also the fact that, well, if we look at the property of the numerical scheme, even if the numerical scheme is mean strong convergent, so it has a strong order 1, well, the property of the numerical scheme are not so nice to some extent. Why? Well, because whenever we talk about weak or strong error, we are talking about asymptotic results, right? We are talking about what happens to the numerical scheme when the time step goes to 0. But in fact, we are dealing with, whenever we simulate, we have to fix a positive, a strictly larger time step. So what I'm plotting here is, for example, the invariant distribution that I obtain when I simulate my trajectory with the tame Euler-Maruyama. Now, I told you that this type of SDE admits it's geometrically ergodic. What does it mean? It means that no matter where I'm starting, the distribution of my process converges exponentially fast to the invariant distribution. So imagine that I'm simulating one trajectory from this model between 0 and sometimes t equal to 10, let's say. So all these points are observation from the invariant distribution. So what I can do is plotting an empirical density of them, which you can imagine as a sort of smoother histogram of this realization, okay? And, well, ideally, we would like to have the same estimated invariant density for different value of the time step, right? This would be a way of saying, well, our derived numerical scheme is robust because no matter how small or how large is the time step, the results are consistent. This is true for these two cases that yields the same invariant density for a time step equal to 2 times 10 to the power of -4 in blue, -3 in red, or -2 in black. But if you look at the tame Euler-Maruyama, which remember, it was one of the convergent numerical scheme, or the truncated, or these other modified version of them, well, you can see that if your time step is as large or as small as 2 times 10 to the power of -2, well, we will get that the estimated invariant density is bimodal. So what does it mean? If we don't know anything about the true underlying distribution, as this is often the case, and we simply simulate our process with such time step, what we will conclude is that our process is bimodal. It admits an invariant distribution which is bimodal. Okay? So we will conclude that the membrane voltage of my underlying neuron is equally probable, assuming value around 0.6 or -0.6, while in fact we know that it should be around 0. Okay? So this is an example that even if you have a convergent numerical scheme, even if your numerical scheme is strongly convergent, this doesn't imply that it has nice property for fixed final time step. Because at the end of the day, whenever we simulate, especially if we want to embed our numerical scheme within a simulation-based inference, within inferential algorithm, well, then we need to deal with a positive time step. And you see, the choice of the time step plays a crucial role if the numerical scheme is not robust for different value of the time step. This is another example where you see that all of these are convergent numerical scheme, but they do not preserve the phase of the oscillation. They do not preserve the amplitude of the oscillation as soon as the time step increases. Okay? So obviously there has been some modification. One possibility was, well, why should I stop at Euler-Maruyama that is a order 0.5, right? So if you imagine during the Taylor expansion, the first expansion will be Euler, which in this case would be also Milstein, as the noise is constant. So then the idea was, let's go one step forward. When they did that, they actually saw that the covariant matrix, in the case of the Fitzgerald-Gumo, is not degenerate, so the scheme is hyperelliptic, but is not mean square convergent. So that means that you see, as soon as the time step increases, the dynamics of the process are not preserved. Okay, so this is a phase plot of the two coordinates for different value of the time step. The one on the left-hand side does preserve the dynamics, the one on the right-hand side crashes. So if we use modified Euler-Maruyama schemes, they are mean square convergent, but not hyperelliptic. This other version is hyperelliptic. This other approach based on local linearization yields mean square convergent scheme and one-step hyperelliptic, but none of them is actually able to preserve the ergodicity and the oscillatory dynamics of the model. Okay, so we then were thinking of, well, what should we do? What can we do? And what we came out with was deriving a numerical scheme that belongs to the class of the so-called splitting scheme. The underlying idea is very simple. It's very intuitive, and hopefully I will make it clear. Okay. So, what is the problem? Well, the problem is that we are dealing with an SDE that we cannot explicitly solve. But what happens if we can split it? If we can decompose this initial SDE into several sub-equations, into several SDEs that we can each independently solve. Well, then this will be the step one. So we start from our initial SDE that we do not know how to solve it. We decompose the drift and the diffusion coefficient linearly into a sum in a way that we obtain a subsystem, a certain number of sub-equations, and all of them are explicitly solvable. Then we need to solve them, and this is the second step. And then obviously we are starting from a unique SDE to several subsystems of SDEs, and we need to compose the solution of these individual subsystems in a way that we ended up with a solution for the initial system. So I don't know if this is clear. Hopefully it will become even more clear now. So let us look at our SDE in this nonlinear setting. Okay. So once again, the drift is non-globally Lipschitz. It is semi-linear, so there is some linear components A, X, T, and this non-linear term. So what we can do is decompose this drift and this covariant matrix into some part that is linear, so A plus sigma, and some parts that is not linear, so N and 0. Okay, so what we do is, instead of solving one d-dimensional SDE, we can decide to split that and solve two SDEs, each of them, well, sorry, two differential equations, Each of them is d-dimensional, so the same dimension as the initial SD. The first one is an SD, and the second one is a ODE. Yeah? So if you see, if we sum up the drift coefficient, we get the initial drift coefficient. If we sum up the diffusion coefficient, we get the initial diffusion coefficient. So this is really the idea of splitting schemes. You split the drift f into the sum of as many terms as you want, and similarly for the diffusion coefficient, in a way that each of the underlying subsystem can be explicitly solved. And this is what we are going to do now, because when we start from this initial SD that we don't know how to solve, we then derive a linear SD that we know that is nothing else than a sort of multivariate or Stern-Uhlenbeck that has some explicit solution. Okay. So this might look nasty, but if you look at that, you can see that the solution to this linear SD will be a Gaussian process with this mean and this covariant matrix. Okay. So what does it mean? It means that we are actually able to solve this SD exactly. And what we will have to do is we start from the previous step, we multiply by e to the power of, so the exponential matrix with my time step. And then I need to add this guy here, which is a multivariate Gaussian with mean 0 and this covariant matrix. That's what I have here. Okay. So when doing that, I solve the underlying SD explicitly. Well, then I also need to take care of the underlying ODE. And what I'm doing is assuming that this non-linear ODE can be solved explicitly. If that's not the case, then one might use some Runge-Kutta or some ODE solver for solving this. But again, you see, we imagine that we succeed in deriving the explicit solution of this ODE, and then again we can rewrite that as my solution starting from the previous point. Okay. So we have one solution for the SD, one solution for the ODE. We have way of composing that. And the composition can be in the flavor of what is known as Lee-Trotter scheme or Strang scheme. What is the Lee-Trotter doing? The Lee-Trotter is composing the deterministic solution with the stochastic one, where you go first for the deterministic one with a full time step, and then what you obtain, you plug it in as starting condition in the underlying SDE. The other composition is also possible. One can first have the stochastic and then plug that into the deterministic. The strong one instead suggests to start from the solution of the deterministic with half a time step. What you obtain is going to be the starting condition of the stochastic solution with a full time step, and whatever you get will be the starting condition of the deterministic solution with half a time step. Okay, so we want to go from Ti to Ti minus 1. We don't know how to make the big jump because we don't know how to solve the underlying SDE. So instead, we solve the ODE, the underlying ODE and SDE, and we compose the solution in this way. What is nice is that actually you can prove that what seems like something a bit artificial or not so reliable, robust somehow, it actually possesses some nice property. So in fact, what we did was proving that the Lee-Trotter, so the composition of first you solve the deterministic ODE and then you plug that into the SD solution. Well, that one is yielding a mean square convergent numerical scheme of order 1. Actually, Filipovic, Samson, and Ditlev also proved that the Strang scheme has the same property. So it also admits it also mean square convergent of order 1. So what you see here is an illustration of different numerical scheme yielding different order. So we see that the Strang and the Lie Trotter, which are with black and green, this one, they have a very similar order of convergence as the truncated, and they are all of order 1. Okay? And the tame Euler-Maruyama is also a similar strong order 1. The nice thing is that if you just go back here and you look at what is the transition density of this process given the previous step, well, as this is Gaussian, and this is a constant because we are conditioned on the previous value, we can immediately see that this guy is normal distributed with this mean and this covariant matrix. Okay? But that means that the covariant matrix has this expression. And as long as A is not a zero matrix or is not like 0, 0, 0, 1, this whole covariant matrix is going to be non-degenerate. So what does it mean? It means that our numerical scheme has the check of being mean square convergent and also hyperelliptic. So in the case when sigma transpose is degenerate, we have seen that the modified Euler scheme would yield a degenerate covariant matrix, while in this case, this numerical scheme has a non-degenerate covariant matrix, thanks to the fact that it has the correct noise structure incorporating the behavior of the drift via the exponential matrix. One can also prove that the scheme is geometrically ergodic, so no matter where we are starting, the distribution of the process will converge exponentially fast with the invariant distribution. This was the case with the generic setting. I was telling you that the stochastic Fitz-Nagumo was one particular example within this class. So actually, we had to check that all conditions were fulfilled and the generic theorem could hold. And this is the case. So if you see, we split this non-linear, non-globally Lipschitz drift into a linear component where this is the A matrix and a non-linear component M. And the non-linear component is the one having the non-globally Lipschitz term. Now, as you might immediately see, or maybe not immediate, but as you can see, in principle, this term here is linear, right? 1 over epsilon V is linear in V. So in principle, this 1 over epsilon could enter into this matrix. This will be fine. This would yield a different numerical scheme, but actually it won't fulfill the same nice property as the original one. It will be yielding a little bit some technical problem in the proof of the convergence of the geometric ergodicity. But what you can see here is that as long as the noise propagates through the drift, you see, the second coordinate is the one with the noise, and we have it here. We have this dependence on the rough coordinate into the A matrix, which is the one entering into the stochastic linear SD. So as long as we do that, then what we are going to obtain is a sub-equation that is nothing else than the linear damped stochastic harmonic oscillator, which will yield a multivariate Gaussian with mean and non-degenerate covariant matrix. And the second SD, the second ODE can be solved exactly and explicitly. You see that this would be linear in the U, and one can find an expression for the V component. Now, let me show you how things work. If you remember, in the case of the modified Euler version, the oscillatory behavior was not preserved. So there was some sort of discrepancy in the either in the amplitude or in the phase of the oscillation. While now you can see that the trajectory generated when you fix the random number is the same if you consider different time steps, which is what we would like to see. So obviously, we want a numerical scheme to be convergent, to have a strong error as high as possible, but we want the numerical schemes to preserve the feature of the model for a fixed finite positive time step, which is the case here. And this is also the case if we look at the phase plot. So this is the strand scheme, lead trotter scheme. These are both splitting scheme with two different time steps, 10 to the power of -4 times 2, or 2 times 10 to the power of -2. What you see here is that when we increase the time step, the phase plot, so the dynamics, the oscillatory behavior of the two components, V and U, is similar. But this is not the case for any of the other mean-strong convergent numerical scheme, because what you see here is that when the time step increases, when delta is 2 times 10 to the power of -2, what happens is that the amplitude of the oscillation are not preserved. So in fact, you see that the dynamics are going outside this rectangle. And this is if we look at the invariant spectral density, which is the Fourier transform of the autocorrelation, which gives us an idea of the presence of the autocorrelation between the consecutive observations. What you see here is that, well, again, what we obtain with strand and lead trotter is consistent and robust across a different time step. While, for example, the tame Euler-Maruyama will tell us that the highest value in the autocorrelation, so the frequency of our observation is 2 instead of being 3. And you also see that the peak is quite different. Okay. This is in the case of the invariant density, as we were discussing before. So that's the figures that we saw before. While now you see that if we estimate the density from my simulated trajectory, we will get very similar results for different time steps if we use these splitting schemes. And this is one more illustration of the geometric ergodicity of the numerical scheme. Now, this trajectory has been generated by fixing the random realization. So we are having the same random numbers, okay? And what does it mean that the process is geometrically ergodic? It means that no matter how far you start from 0, the process will converge exponentially fast to the true reference trajectory that will be one realization coming from the invariant distribution, okay? Which is what we observe here. You see, this is the dynamic of the trajectory where we have the reference numerical scheme, and all of them are similarly behaving, or there is basically, except for one numerical scheme, all of them behave the same. If we start pushing one of the coordinates far away from 0, where 0 in this case is the asymptotic mean, or the mean of the invariant distribution, well, you can see that, let me try to zoom in, if I can, yes. You will see here that this gray line, which is the reference one, coincide with the strand and the lead trotter, okay? So we start from 1000, but the dynamics of the process are immediately pushed to the one that is determine, and you see it's exactly the same because that's the dynamic of the invariant distribution. Okay? While if we use Taylor, tame, and truncated Euler-Maruyama, well, this convergence is not exponentially fast. You see that it happens after time 0. Here it happens after time 2, and also it introduced some delay in the oscillation. Okay. The last question is, well, does this really matter for statistics? Hopefully, I try to convince you, and you are convinced that if the initial SD is hyperelliptic, so should be the numerical scheme. If not, then it means that we cannot use that as a sort of likelihood. We won't have a two-dimensional random object if we are dealing with the Fitz-Gumo, but we will only have a one-dimensional random object because the noise will only enter in 1 instead of 2. But if you imagine embedding this simulation within a simulation-based inference scheme, for example, like ABC, so approximation computation, what you see here is that the inference of the posterior that you get is correct across different time steps only if you use this splitting scheme, which is this dashed brown line. While if you simulate the trajectory from the Euler-Maruyama scheme, your final inference will be quite far off from the true value, which is lambda equal to 20, and might strongly depend on the value of the time step that you choose. Now, I mean, this is just to give you a snapshot. The underlying key idea is that if you want to simulate this trajectory and you want to use that within an inferential algorithm, well, the results of your algorithm, in this case the posterior, will be strongly affected in a negative manner if the underlying numerical scheme is not good enough. So to wrap everything together, we derive some numerical schemes that we show are one-step hyperelliptic, satisfy some Lyapunov condition. They are mean square convergent, geometrically ergodic, and preserve the oscillatory dynamics. Okay. One of the, well, three of the take-home messages is that even if you derive a numerical scheme that is strong convergent, it will still be important to check the property of your scheme for a fixed finite time step, because this is what you use when you simulate. This is what you use if you want to use your algorithm within some inferential approach, or even if you want to simulate a trajectory to study the behavior and the property of your model in case you do not have any theoretical results. The other message is that even if your numerical scheme is strongly convergent, things might be wrong. And there can be cases where no matter how small is the time step, things can be wrong. So choosing a small time step not only can be very bad in terms of computational timings, but might not solve the problem if the numerical schemes does not preserve a certain feature. Okay. This is a list of reference. Most of the talk is based on this paper with Evelyn Bukvar and Adeline Samson and Irene Tubikanets that has been published last year in Applied Numerical Mathematics. A very nice paper deriving some higher order splitting scheme is the one by Foster, Gonzalo dos Reis, and Strange, where they derive some strong 1.5 error schemes. But we are actually working on checking the property for finite time step. If you're interested on the Fitz-Gumo model itself, this could be some relevant references. This one is a recent one. It is also having some numerical results because in this paper they proved that also the strong numerical splitting scheme is mean square convergent of order 1, exactly as Lee-Trotter, but it has a higher weak error order than Lee-Trotter, which is something that we observe experimentally, but they succeed in proving. And with that, I'd like to thank you all for your attention, and I will welcome any questions if you have any.
Thank you, Massimiliano. Sorry. Thank you, Massimiliano, for this very nice talk. Are there some questions, please?
Sorry, I cannot hear you.
Could you hear me, please?
Yeah, now yes. Yeah.
Okay. Thank you for this very nice talk. Thank you, Massimiliano. Are there some questions, please? Today we have many specialists in numerical analysis and in PDEs. Maybe they have some questions, huh? Hello? Nabil, you can hear me, right?
Yes, yes, I hear you, yes.
Okay. Okay. Meanwhile, I personally have a question. Why, since the beginning, you have to specialize the shape of your SD with the cube, with the square? If possible, if you can go back at the first 3 pages, please, or maybe the yes, that one. So yes, the one after. Sorry. Yes, is that cube in the V? Is it so important?
Yeah. So this term here arise from a modeling point of view. So this fictional UMO, the deterministic and the stochastic version, has been used for describing the behavior of the membrane voltage, that has been used for kind of combining the dynamics that you observe, something like this, with what the model can reproduce. The fact that there is this term is what makes the numerics challenging, because this overall drift is non-globally Lipschitz, so that means that it's going to explode if you don't treat it properly. So if there was here a linear component or something that was smoother, then the drift would have been globally Lipschitz. One could have used Euler, and Euler would have been strong, or I mean, would have had a strong order 1. But due to the fact that there is this V to the power of 3, the underlying drift coefficient is not globally Lipschitz, so the canonical Euler-Maruyama scheme would fail in terms of strong error, and then this will make the analysis more complicated.
And if you let epsilon to infinity and get rid of that term.
Yeah, but if you let epsilon to infinity, you will kill the whole
Yes.
trajectory, right? So epsilon has to be finite, and typically, actually, epsilon is small because it is describing how the V and the U components change and switch. It's a sort of time scale parameter, assuming small values.
Okay. So are there other questions, please?
There is a question in this chat, Wissam.
Where? Sorry, in the chat.
The chat, yes.
Yeah. So the question is there exist another scheme instead of splitting scheme? in principle, I mean, you can derive, you can come up with the scheme that you prefer. Another class of scheme that can be useful for similar model, similar type of process could be the one of log ODE or linear ODE that are from the group around Terry Lyons and Foster, where the idea is to switch from a Nito SD into a Stratonovich SDE, map that into what is known as control deterministic equation, and solve that. So this would be a different type of numerical scheme, but then one will have to check whether the property are preserved. So in general, this is not something that you will have to go setting by setting because the technicalities might differ and a numerical scheme might be better or might be more suitable in a certain setting than another one.
All right, Professor. Thank you. I got your point. Thank you very much.
Thanks for your question.
Okay. So are there other questions, please?
Sam, can I ask a question, please?
Of
Yeah,
course.
of course.
Yes, thank you so much, Massimiliano, for the nice talk. Actually, maybe I missed it a little bit. In the conclusion, you say that even a refinement cannot solve maybe the problem or numerically, right?
Yeah. So when I was talking about this.
Yeah, in the conclusion, the page before. Yes.
Yes. Yeah. So you mean this point?
Yes. Right. Yes.
Yeah. So what I mean is, if you think about the case of the Fitz-Gumo, when there is only the noise entering one coordinate, if you write down the covariant matrix, here you will get something that is not zero. Okay. So in this case here, if you use tame Euler or truncated Euler, no matter how small is your time step, here you will always have zero. Yeah. So you can choose the time step as small as you want, but this will always be zero, while in fact you know that this number should not be zero.
Right. Yeah.
Okay. So this is one possible example of a situation where no matter how small is delta, things will not work out. And there can be also some cases if you have again a one-dimensional SDE that is similar to the first coordinate. Imagine that you just have dwt, and here there is this minus xt term, minus b3 term. What happens is that you can show that this solution, this SDE is geometrically ergodic, but if you consider Euler-Maruyama, no matter how small is your time step, you can always find a starting condition such that the scheme explodes. So this is to say that in general, even if the time step is as small as possible, there can be situations, as in the presence of hyperellipticity or the example that I quickly mentioned now, where the SDE, where your numerical scheme will explode or will not have some property that it should have.
So basically, it's due to the cubic term, the semilinear term,
Yes.
right?
Yes. In this case, the explosion is due to the cubic term, while let me quickly do this. While in the case of the in the case that I was mentioning before, the hyperellipticity, that's due to the noise structure. The fact that the noise enters only one coordinates, but if you use Euler, it doesn't propagate in a correct manner. I was trying to. I'm trying to see if I can find. Let me see.
Wissam, may I ask a question, please?
Yeah, of course.
Yeah. Thank you very much, Dr. Massimiliano, for this nice presentation. So actually, maybe I missed the beginning of the lecture, and I'm worried about the motivation behind the considering some irregular or some not really smooth coefficients in multidimensional SDEs. I mean, for example, there's some motivation from industry, from concrete problems, from physics, from other disciplines. That's my words.
Okay, let me try to share again the screen. Let's see if I. Yeah, so in this case, you mean why the noise enters only in some of the coordinates?
Sorry?
So your question is on why the noise enters only in some of the coordinates. What's the reason for that?
No, I mean, for example, when you have this non-Lipschitz coefficients, the singularity comes here somehow in the explosion of the solution, maybe for some coefficients, and also there is some particular forms of the because you are considering so far additive noises, and you have discussed also some nonlinear coefficients at the end. But my worries was what were are there some motivations from industry, from physical problems, from where such kind of coefficients appeared naturally in some problems.
Yeah, so I mean, this is an example of an SDE or a ODE, depending if you want to consider the deterministic case, that has some application coming from neuroscience or biology. But in general, other type of, I mean, if you consider the SDE where this term is zero and you only have this minus V3 component with some additive noise, then this will have some application also in other fields. So the point is that we were driven by this example that is coming from neuroscience, but the same thing will hold if you consider the van der Pol oscillator. So oscillators are very common if you think about biology to describe some cardiac behavior or to describe EEG data or things like that in neuroscience. And this is where
Thank you very much.
Wissam?
Like this regarding stochastic processes. I said this before about that I used it with blood flow, platelets, blood flow in the vessels, in the human vessels. And at that time, we had to find some kind of gradient and set the gradient to 0 in order to be able to reach some computation, I could always, send to Massimiliano or to Nabil, as I did before, the PDF or the various aspects of this. But we discussed this problem since 1991. Anyway, I thank you very much, Massimiliano. I thank very much the people that asked these questions. Jazakumullah khair. Nice afternoon to everyone, inshallah.
Okay, thank you. Thank you. Are there other questions, please?
So I just want to comment that I mean, in principle, from a theoretical point of view, everything is known, but what you don't know from a theoretical point of view is actually how to, for example, you know that it exists an invariant distribution, but you don't know how it looks like. So you know that your process admits an invariant density, but you have no clue of saying how this invariant density looks like. Is it Gaussian? Does it have a different shape? What is the correlation between the V and the U? So you only have some global information on the fact that you know that it exists an invariant distribution, but you don't know how it looks like. So that's why then you need to simulate from the model. And that's where then the problem might start.
Okay, thank you. So are there other questions, please? You can hear me, Nabil, right?
Yes.
Okay. Then if there are no questions, we'd like to thank so much Massimo for this nice talk.